Hello, welcome to this review lecture on AC circuit analysis. We'll go over three examples that cover nodal analysis, loop analysis, and Thevenin theorem for AC circuits, and we'll explain how we can solve these circuits using the phasor techniques we learned during the course. This is the first example we have here. We have a circuit that has these components, and you should notice here that we don't know what is the frequency. This term here is j omega L. So omega L for this inductor is equal to 10. So the calculations have already been made for us, and they are giving us the impedance directly of these components. So j omega L for this one here is J10, j omega L for this inductor is J30, j omega L for this inductor is J60. Okay, so we'd like us to use nodal analysis to find the output voltage, and if the frequency is 1 kilohertz, they ask us to convert V note from its phasor form to its time domain form. Okay, so the way we're going to do this, we're going to define this node here as V1 and this node here as V2. This is going to be ground, okay, and then we write the equations governing the two nodal voltages V1 and V2, and we solve two equations and two unknowns. We have only two nodes here, V1 and V2, and this is ground here. So this is going to be our reference. So for the first node, this one here, we're going to see that the sum of all currents flowing out from this node are equal to 0. This current here in the flowing in the outward direction is V1 minus the source divided by 20 ohm. So this is this term here. This current here in the flow which is flowing out from this node, or at least its reference flowing out, is V1 tilde divided by J10, which is this term here. This current here in this direction, the outward direction from the first node, is V1 minus V2 divided by 40 ohm. So this term, the sum of all these three currents must be equal to 0. Once you have written this equation, you collect the similar terms. So the terms multiplying V1, and here I put tilde on top of it just to indicate that it's a phasor, but I don't have to do so. I could have simply written it as V1, but it's already understood that this is still a phasor. So I have here 1 over 20, I have here 1 over J10, I have here 1 over 40. So we collect these terms together, and remember 1 over J10 is minus J over 10. The only term that has V2 is minus 1 over 40, so we have this term. We move minus Vs over 20 to the right hand side, becomes Vs over 20, and Vs is 10 angle 30. If you divide 10 angle 30 by 20, you get 0.5 angle 30. So we're gonna now start to collect coefficients. This will give us 1 over 20 will give us 0.05, 1 over 40 will give us 0.025. So the sum of these two will give us 0.075. This is minus J.1, and 1 over 40 will give us 0.025. So we have that here, and this is the source term divided by 20. Just to simplify things a little bit, I multiplied both sides by 10 just to make the numbers a little bit bigger. So this becomes 0.75, this becomes minus J.1, this becomes minus 0.25 V2, and this one becomes 5 angle 30, and 5 angle 30, if you expand it as 5 cosine 30 plus J sine 30, you get this complex number here. So this is my first equation. This is the equation governing V1 and V2. This is the coefficient of V1, this is the coefficient of V2, and this is the right hand side coefficient. Of course, from this one, I could write V2 as a function of V1, and what I did here, because this is 0.25, I multiplied both sides by 4. So this becomes 1, and I moved V2 to the right hand side, and I moved this constant term to the left hand side. So everything, when you multiply it by 4 and you move this term to the left hand side, this is the expression relating V2 and V1. We're gonna later use this expression to eliminate V2 and have only one equation in V1. Okay, we write the KCL at node number 2 here. So we say the sum of the three currents flowing out from this node are equal to 0. This current here is V2 minus V1 divided by 40. This current here is V2 divided by J30. This current here is V2 divided by this impedance, this combined impedance to ground. So this is V2 divided by 30 plus J60. So I wrote here all these three currents, okay? And what I'm gonna do now, I will start to collect the coefficients of V1 and V2, and remember we have to do it in order, otherwise we can make a mistake if we put in a matrix form. So the coefficient of V1 here, I have only one coefficient, it's minus 1 over 40. The coefficient of V2, I have 1 over 40, I have 1 over J30, I have 1 over 30 plus J60. So I have three coefficients multiplying V2, and this is equal to 0. 1 over 40 becomes 0.025. 1 over J30 becomes minus J over 30, so it's minus J 0.0333. 1 over 30 plus J30, you can simplify this term by multiplying with the conjugate. So what I can simply do here, I can simply multiply by the conjugate to the denominator. This becomes 30 minus J60 divided by the modulus squared, so it becomes 30 minus J60 divided by 900 plus 3600. Okay, so you divide them, you divide each term here, divide 30 by this number, which is 4500, divide 60 by this number, which is 4500, you end up with this complex number, 0.0067 minus J 0.0133. So this is the second equation relating V1 and V2, and we can simplify it, of course. We add this real part, we add this imaginary part, and then we have one equation relating V1 and V2. This will be our second equation. So we did that here. We wrote the equation here. I collected all the coefficients. So a coefficient multiplying V1 plus another complex coefficient multiplying V2 is equal to 0. And just to make things, again, the numbers more reasonable, I multiply both sides by 10. So this is the second equation relating V1 and V2. I could have written the two equations in a matrix form, and I used any program like MATLAB or my calculator to solve a complex system of equations in two unknowns. But what I did here, I removed V2 and I replaced it from equation 1 by the expression we derived earlier, but by 3 minus G4 V1 tilde V1 minus 17.32 minus J10. So you can see here, this is still the same, this bracket is still the same, but I got rid of V2 and I wrote in terms of V1. Now I collect all the terms related to V1. I have how many terms related to V1? I have, this is a term related to V1, and this bracket, multiplying this bracket, will also be related to V1. I did this using my calculator. So you multiply this with this will give you a real term. This will give you a real term. This will give you this one will give you an imaginary term. Multiply this term by this term will give you an imaginary term. So I collected all these terms multiplying V1 in addition to the minus 0.25. I end up with this term here. Okay, and the other term on the right hand side, you multiply this term here, which is 17.32 plus J10. There is a negative sign outside. You multiply it by this bracket, and then whatever you get, you move to the right hand side. And this is what I did here. Okay, so it takes just some calculation with your calculator. You can do it, of course, if you have a complex calculator, you can switch your calculator to a complex mode, and then you do the solution. Now the problem is some complex coefficient multiplying V1 is equal to some constant, then V1 is equal to this complex constant here divided by the complex coefficient, and you can do this division using the modulus and the angle, or you can do the conjugate, or you do it using calculator as I did here. I used my calculator and the answer I got was 0.289 plus J 4.0189. I strongly encourage you to verify all these numbers. I double check them, but please double check them using a calculator. So if you are not sure how I got this answer, pause the video for a second and then try to maybe use the conjugate of the denominator, or try to convert these two both into modulus and angle, and then divide the two moduli and then subtract the two angles. All of them should give you exactly the same answer, which is this one. So we got V1, and now we are back to get V2. So V2 is equal to this coefficient multiplying V1 plus this constant. We had this equation earlier. If you multiply this one by this one and then you add this complex number, you obtain this one here for V2. I'm not going in detail through the calculations. I did them outside with my calculator, and I strongly encourage you to verify them. Now I found V1 and I found V2. We still need to get V output. V output is not V2, but you can see here there is a voltage divider because V output is simply equal to V2 multiplying J60 over J60 plus 30. Okay, so this is what I did here. I got V2, I'm gonna apply voltage division. So I multiplied by J60 over J60 plus 30, and then I multiplied by the conjugate of the denominator. So I multiplied, and please don't make the mistake, see the conjugate is 60 minus J30. You have to write it as in the form of real plus J imaginary. So this is 30 plus J60. Then the conjugate is 30 minus J60. I've seen this mistake already a couple of times this term. Okay, so I multiply by the conjugate. This becomes 900 denominator. This gave me 3600. And when you multiply all these numbers 1, 2, 3, and then you divide them by this constant, you obtain this expression for the output voltage. And this is what, and I got this through my calculator, and I did not have to really convert it to polar form or to denominator form. So just get the answer, get in a correct way, and this is the final answer you should be able to get for the output voltage. Of course, this is the expression for the output voltage in polar form. You can put in polar form as well. Okay, and once you have the polar form, to write it in the time domain, this is the amplitude and this is the phase. So it's going to be the amplitude cosine omega t. Omega is 2 pi multiplying 1k, so it's 2000 t, 2000 pi t. Okay, so this is, can you remember frequency is 1 kilohertz. So this is 2 pi multiplying frequency, so this is 2000 pi multiplying t plus the phase shift. So this is the phasor diagram of the problem. This is the input voltage. It is 10 angle 30. So it's an arrow. It has a length of 10. It makes an angle 30 with the real axis in the complex domain. While the output is only 0.8735, okay, and it makes the angle 139. So it looks something like this. It's a little bit shorter arrow because this is only 0.8 while this one is 10. But the V naught leads V input. Okay, so this one leads, if you draw the two cosine functions, this one leads here in time. Okay, let's take a look at one more example. We are giving this circuit and we are asked to use Thevenin theorem to calculate the current I node. This is the current flowing in this output resistance. Okay, so the way we are going to do it, the same way we did it for real circuits, we are going to consider this as our load. We are going to get the Thevenin equivalent. First, we create an open circuit between these 2 points to calculate V Thevenin. V Thevenin is V open circuit. And then we remove all the sources, and then we'll try to find the input impedance seen into the circuit, and this will give us Z Thevenin. Of course, here we talk about the Thevenin impedance, not the Thevenin resistance. Once I have them, I can replace this whole circuit with its Thevenin voltage and Thevenin impedance connected in series with this 10 ohm. Remember that this 10 ohm is not included in the calculation of the Thevenin equivalent because they simply represent a load. It does represent a load for the Thevenin circuit. So first thing I'm going to do, I'll now create an open circuit here, and then I'll try to calculate the open circuit voltage. So the open circuit voltage is this one. So what we have here in this circuit, a current source. It's injecting current into one impedance. I called it here Z1, so I call this one here Z1, 5 plus J5. And then another impedance in parallel, which is this branch here. This is a 15 plus J5. Okay, so if you get the total impedance, and you multiply it by this current source, you'll be able to get this voltage here, this voltage between here and here, okay, between this point and this point. Okay, and then you can use current division, voltage division, to get V output or the open circuit voltage in terms of this voltage. So this is what I decided to do. I'm gonna combine these two parallel impedances, 5 plus J5 in parallel with 15 plus J5. Okay, and I'm gonna multiply them with the current source to get this voltage here. Okay, and once I have this voltage, I'm gonna use current division between 5 plus J5 and 10 to get the open circuit voltage. So let's first get the total impedance Z1 in parallel with Z2. So 5 plus J5 in parallel with 15 plus J5. So this one in parallel with this one. Okay, the way I multiplied it, I did this more and more detail. So 5 by 15 will give us 75 minus 25, then you have 50 real. This will give us J75 plus J25 get J100. In the denominator we have 20 plus J10. We'll multiply, what we can do, we can eliminate 10 from numerator and denominator just to make the numbers a little bit simple. So this becomes 5 plus J10. This becomes 2 plus G1, and then we can convert these two to their polar form. So the modulus of this one is square root of 5 squared plus 10 squared. This will give us 11.1803, and the angle is the inverse tangent of 10 over 5. This gives us 63.43 degrees. For the denominator, the modulus is square root of 2 squared plus 1 squared, square root of 5. You get 2.2361. And the angle is the inverse tangent of 1 over 2 will give us 26.56. So you divide these two complex numbers, you divide the moduli and subtract the angles. So this one by this one will give us exactly 5. And if you subtract this angle and this angle, so subtract this one from this one, you subtract the numerator from the numerator, you obtain 36.86 degrees. So this is a total input impedance, and this of course is in ohms. And now I'm ready to multiply this total input impedance by the current to get this voltage here. Okay, to get the total voltage, because remember this Z1 in parallel with Z2. So when they are in parallel, then you have the same voltage across them, which can be obtained multiplying the current source with the total impedance. So we move now, this is the last step. I'm going to multiply this current source here by the total impedance to get the voltage V1. I called it here V1. The source is 5 angle 30. The impedance is 5 angle 36.86. And when you multiply two complex numbers, you multiply the moduli and then you add the angles. And this is what I did here. 5 by 5 will give us 25. This one plus this one will give us this one. Okay? So if I want to get Thevenin, which is open circuit voltage, is equal to V1 multiplying 5 plus J5 divided by 5 plus J5 plus 10, because this is really a voltage divider, just a voltage divider between this impedance and this impedance here. And this is what I wrote. V open circuit is Thevenin, is the voltage V1, which I already calculated, multiplying 5 plus J5 divided by 5 plus J5 plus 10. So you get in the denominator 15 plus J5. So I converted all these numbers to their polar form. So this is V1, this is 5 plus J5 when I convert it to polar form. This is 15 plus J5 when I convert it into polar form. Okay, I'm going to multiply the three moduli. I got this number here. I'm going to add this angle, and then subtract this angle. I got this angle here. So this is my Thevenin voltage. Okay, so we can do that. So the next step is to proceed to find the Thevenin impedance. And to find the Thevenin impedance, we'll create an open circuit from the load side and then remove the only source we have. So you can see the current source has been eliminated. So looking from this side, what you see 5 plus J5 in parallel with 15 plus J5. Correct? But these are the two impedances. The circuit is symmetric. So when you look from it this way, it will give you exactly the same impedance as when you look at it from this way, but after you remove the current source. So 5 plus J5, this 5 plus J5 in parallel with 15 plus J5, but this we calculated this impedance earlier. This is the total input impedance seen from the left hand side. So we have that number. It is 5 angle 36.86. And by the way, if you convert this number to a rectangular form, you get 4 plus J3. So 5 multiplying cosine 36.86 will give you 4. 5 multiplying sine 36.86 will give you 3. So the last step in this question, we already found the Thevenin voltage, we found the Thevenin impedance. We connect now the load and we use this equivalent circuit. Then the I note we are looking for, the current going through the load, is V Thevenin divided by Z Thevenin plus RL or ZL. Doesn't matter, it's real here in this case. So we calculated our V Thevenin, it's 11.18. We calculated Z Thevenin. It was 5 angle 36, but when you convert that to rectangular form, you get 4 plus J3. Then you add 4 plus J3 to 10, you get 14 plus J3. You convert this one to polar form. So the modulus of this term will be square root of 14 squared plus 3 squared. You obtain this term here. Okay, and then the angle is inverse tangent of 3 over 14 will give you this angle here. Okay, and then you proceed to you divide these two complex numbers, and then you obtain this number here. Okay, so this will be the current flowing in this circuit. It's 0.7808 angle 81.3. So if you are given the frequency, you can write it as 0.7808 cosine omega t plus 81.3 degrees. Okay, let's consider our last example. We are given this circuit and they are asking us to find the currents I1, I2, and I3 using loop analysis. And they want us to find the ratio between I1 and the I3. Okay? Okay, so we're gonna do loop analysis. We're gonna consider every loop. We'll write KVL, and we'll get 3 equations and 3 unknowns, I1, I2, and I3. We can do elimination or substitution to convert them to only 2 equations, 2 unknowns. But as I said in class, in most of these problems, if you write the system of equations, you'll get pretty much most of the mark, as long as you did everything in a correct way. But of course, sometimes we ask you for other things, like calculating a voltage drop or something, so you're probably getting the currents. You have to know how to do that through either Gauss elimination or using your calculator or using direct substitution, whatever the case it is. Okay, so we start to write KVL for loop 1, loop 2, and loop 3 to get 3 equations and 3 unknowns. So let's go around the first loop. So here Vs, and as I mentioned in class, when I consider the first loop, I take all the drops to be positive in the direction of the current of that loop. Okay, so here I'm going in the clockwise direction, so I can consider this positive. So Vs minus this drop, so this is minus J2 multiplying I1, minus this drop, so and this is 5 ohm multiplying I1 minus I2. So this is my first equation. We collect all the coefficients, we put them in order. So minus J, I have here, I'm gonna move all the coefficients to the other side, and I will keep Vs there. Vs is equal to 10. So the coefficient with I2, I have 5 and I have J2. When I move them both to the right hand side, they become positive. Okay, I have here plus 5 I2, you move it to the right hand side, becomes negative. And I had it here 0 I3 because I have 3 equations, 3 unknowns. I should not forget about the third unknown. Let's go to the so this is the first equation here. We go to loop number 2, and when I consider loop number 2, as I said earlier, I'm going to consider the drops to be positive in the direction of the current of that loop. Okay, so we'll go now in the clockwise direction. So this is minus 5. This drop is negative, so I'm going to give it a negative sign, and the drop itself is 5 I2 minus I1. So this minus 5 I2 minus I1. We'll continue to go in the clockwise direction. This is going to be negative as well, and the drop itself is minus J4 I2. So it is minus J4 I2. Now we go the third drop. This drop here is J2 multiplying I2 minus I3. But it's a negative drop, so it's going to be written as minus J2 I2 minus I3 is equal to 0. What remains is to collect similar coefficients. So I have here 5 I1, okay. For I2, I have minus 5 here, I have plus J4 here, I have minus J2 here. So I collect them together. For the third current, I have plus J2, okay. So if you collect these one together, J2 minus J2, you get plus J2 here. You get J2 as shown here, and then this becomes my second equation governing the second loop. So we have now 2 equations, 3 unknowns. We go to the third loop and then write the third equation. Okay, in the third loop, here it is. I'm going to take the drops to be a positive in the direction of the current of that loop. Okay, and then I will go in the clockwise direction. So this drop will be considered negative. So this is minus J2 multiplying I3 minus I2. And this drop also be considered negative. This is minus 5 multiplying I3. So these are the two parameters here. I don't have I1, so I'm gonna include it here with an or coefficient of 0. For I2, I have here plus J2 I2. For I3, I have minus J2 I3 minus 5 I3. Okay? And from this equation, I actually can write I2 as a function of I3 because I can divide both sides by J2. So this becomes minus 1 and this becomes J2.5. So you move them to the other side. This becomes the equation governing I2 and I3. I could use this equation to eliminate I2 from equation 2 and equation 3 to have only two equations and two unknowns if I want to, okay? But what I did here, I simply used my calculator to obtain a solution for these three equations, equation 1, equation 2, and equation 3. So I put everything now in a matrix form, so you can see these are the coefficients from equation 1, coefficient equation 2, equation 3. This is the right-hand side, okay? And when I inverted this matrix and I multiplied with this one, I was able to obtain these three solutions. You can as well do Gauss elimination, by the way. So you can divide this equation by 5 plus J2 to make the coefficient here 1. And then you multiply this equation by minus 5 to make this 0. You can do Gauss elimination the same way, but everything is going to be complex here. Anyway, I did using my calculator. I got this I1, this I2, and this I3. Okay, and then the remaining part for this question is to get the ratio between I1 and I3. So this what I did here. I divided I1 and I3. This I1 and I3. I put them both in polar form. Remember, this one has a negative imaginary part. Okay, so this one is in the fourth quadrant. So be careful when you get to your calculator. Your calculator will give you an answer actually the answer with calculator will be fine because it will give you a negative angle, which is okay. This one also will give you a correct answer from the calculator. So this is the modulus of this complex number. This is the modulus of this complex number. I got the two angles. If you divide this one by this one, you get exactly 3. If you subtract this one from this one, you get exactly minus 90. So the surprising thing here is that this circuit makes the current in the third loop exactly 1/3 of the current in the first loop in terms of modulus. So both of them are sinusoidal signals, but the current in the first loop has an amplitude 3 times higher than the current in the third loop, and the phase shift between them is minus 90 degrees. Okay, so this one here, it can be used to create a phase shift. So one of them has a higher 3 times the amplitude of the other, and the phase shift between them is minus 90 degrees. Okay, so if one of them is a cosine, the other one will be a sine, depending on which one you are taking. Okay, so just remember, this circuit is very interesting because regardless of the excitation, actually, you are going to get this relationship. The ratio between I1 to I3 is going to be 3 angle minus 90, which is minus J3.